you want to listen. Recording is activated. It's time for us to solve some problems.
Sharp pencil, sharp
Chapter
mind.
15, right?
Chapter 15, yep.
Do you guys have the numbers written down?
Yes.
Oh, it was what, 45?
Okay, Morgan, what's our first problem?
45.
Yeah, 45.
In chapter 15, right? Okay, this is going to be kind of a crappy homework because we haven't quite covered the material yet, but who cares? We can still get through it together. I got my book here. Let's go over to chapter 15.
It's the spoon from Toy Story 4.
What are you talking about?
I'm talking about the spoon from Toy Story 4. It's right here.
Can you translate that for a 41-year-old who's never seen?
Isn't he a spork, not a spoon?
Forky.
Gosh. Yeah, but
You
that's not a
better
sport.
give Forky some respect.
I'm sorry, Morgan, what was that number again?
45.
45, okay.
Oh.
Okay.
I needed to turn the light on. There wasn't enough power for my
On something,
my calculator.
do you guys have a little ruler handy? We're going to make a table out of this one because tables are nice ways to organize information. So this is homework number 7, I think. We're starting off with chapter 15, number 45.
Yes.
And this problem is about something you're going to learn about on Monday, the Hertzsprung-Russell diagram, or the HR diagram. And we're being asked to compare two stars on this diagram. I'm going to show you guys on the screen in a moment. So I want you to make some columns, okay? The first column will be our star. And actually, you know what we're going to do? No. We're going to do it like so. We're going to have 1, 2, 3, 4. Go like this. Okay, make 4 columns. The first column will be for the property of the star. The second column will be for a star named Proxima Centauri, one of the closest stars to Earth. I'm going to call it Proxima Cent. The other star is Sirius, the brightest star in the sky. And then the last column will be for their ratio. And we're going to compare some of the key properties of a star so that you guys can see that we can gather so much information from the HR diagram. The HR diagram is like the astronomer's version of the periodic table of the elements. It's the periodic table of the elements, but for stars. So we're going to have a column here for...
What does the one in red say?
The one in red?
Yeah.
Proxima Centauri.
Yeah, let me write that better. That's no good. Is that better, Morgan?
Oh.
Hey, did I spell that right?
No,
I did
you're
not.
missing a T.
No.
Yeah, sorry. Man, as soon as I start drinking that iced tea, everything goes to hell.
Is my mic working?
Oh, whiskey.
Yes.
Okay.
Yeah, we heard
Absolutely.
you, Sal.
Okay.
The first row here is going to be for mass. Then we'll do a row for luminosity. These are the key properties of a star: the mass, the luminosity, the radius, the temperature, we'll also do the color, and we'll do the lifetime. You guys got all this? Can you guys see that, Jazz?
Yes.
Yeah.
All right, when everyone's done getting that all in order, we're going to look at the HR diagram, and you guys are going to help me get these values, okay?
Yep.
So I found a ruler, a new one that has centimeters on it,
Oh, cool.
but
Welcome to the metric party.
it's so faded I can't even read it at all.
Oh, man.
Oh.
Yeah,
well,
me too. I have this really big ruler. I just don't know how big it is. It's pretty big.
We don't need to measure anything, guys. You just need a straight edge.
Oh, okay.
That's all we're doing here. We're not measuring anything.
I think it's a meter.
I doubt it. This is a meter, bud. Is your
Yeah,
ruler-
see, hold up. See, it's like,
Guys, don't have a ruler measuring contest.
see, look.
That's in the official homework. I'm sorry.
Hey, are you guys good with this chart? Or Hope, are you still working? Hope's good.
Almost done.
All right, I'm going to show the diagram now. Share screen. Just a moment here. Let's find ourselves an HR diagram. Should have it here. Here we go. Slide 2. Function F5, slide 2. Let me verticalize your boxes here. Okay, guys, I want you to help me here. So can you find Proxima Centauri and Sirius on this graph for me? Where are they? Circle them with your little notation. I know you guys like to draw all over these pictures, right? Can you guys find them? There's Proxima Centauri. No, that's Sirius B. Unfortunately, we're looking for Sirius A. Sirius B is its, oh yeah, okay.
How do you draw on the screen?
Up at the top, there's a little button called annotate. And you can just, oh cool, everyone's annotating. All right,
Oh, God.
I can erase you too, so that's cool.
You can't give us this much power.
Annotate.
Oh, I got an idea, hold on.
I'm on Mac, so it's a little different.
With
Oh.
great power comes great responsibility, guys. Come on.
Okay, so let's answer our question, right? What's the mass? Where do we see the mass?
Down.
Where do we see the mass?
Wait, I gotta like my thing's blocking the whole diagram.
Mass has to be generated from down going up.
Oh, here we go.
Proxima
now I got it.
Centauri is 0.1 solar radius.
Hold on. 0.1. Where do you see 0.1 solar radius?
The diagonal lines going across the diagram.
Oh, okay. Fine. All right, fine. Let's do that then. So if you want, we can do that. So it's 0.1 solar radii for Proxima Centauri. I'm down with that. How about Sirius? What's the radius of Sirius? Radii are measured along these diagonal bars. And this is a logarithmic scale. So that's 1 solar radius. That's 10 solar radii. So what would you say Sirius is?
Like maybe 4.
11 radii.
What the fuck are you
4.
talking about? It's between 1 and 10.
Oh wait.
What the
4
hell?
solar radii.
I got him.
Oh, a pen? Match up.
10 to the first power.
10 to the first power is 10. It is clearly not at 10 solar radii, right? You have to move diagonal. 3. Riker, thank you for being a reasonable person. 3 solar radii. What's the ratio? What is 3 divided by 0.1? Oh my God.
30 times.
Thank you. 30 times.
30.
Y'all got that? Move fast.
Yeah.
I'm going to start moving fast now. Okay, let's get the mass.
Oh yeah.
The mass is printed in kind of purpley colors here, although this one's kind of red for some reason. What's
Yeah.
approximately the mass of Proxima Centauri?
Is that a 3 or a 2? I can't read that one over Vega.
That's a 3.
That's a 3.
Is it 0.1?
I would say
The
2,
mass of this-
2.5.
Yeah, actually, that turns out to
Yeah.
be exactly correct. If you look at the Wikipedia. Let's, so Sirius is 2.5 solar masses, and Proxima Centauri is about 1/10 of a solar mass. What's the ratio there?
25 times.
All right. Let's get their luminosities from the y-axis. So if I take my annotate here and I go to draw, if you start with Proxima Centauri, you can kind of go across the y-axis. What do we see there for the luminosity?
10 to the -3.
And how about Sirius? Oh, I like Sal's.
Sal's very
that's 100. So
Sally's very bright.
50.
yeah, I think it actually turns out to be 30, but it sure does. It kind of does look like 50 here, huh? Let's go with. I think the correct answer for Sirius is 25 times, actually.
So what was Proxima Centauri? 10 to -3rd?
Yeah. So here for luminosity, we have 10 to the -3 solar luminosity units. And I believe Sirius actually turns out to, it did look like 50, but I happen to know the correct answer is 25 times that of the sun. What's our ratio there? Can you do that in your head, Riker?
Do it, nerd.
2.5.
I thought that was really mean.
I can't do that one right off the top of my head.
Oh, come on. 10 to the -3 is 1,000. You mean you can't do 25?
Isn't it 25 times?
No, 10 to the -3 is the same thing as 25 times.
25,000.
Thank you.
Oh.
25,000. Oh.
Thanks,
I
Nathan.
like that.
You rule.
Yeah, didn't think of it like that.
Well, now you do, don't you? You got to learn how to speak scientific. You guys were talking a tough smack earlier about scientific notation, how good you were, and now you can't even do things like this?
Juju.
Well, I was looking at the answer for Proxima Centauri, and I was moving the decimal point.
Say that?
I was looking at Proxima Centauri's luminosity. I was moving the decimal point three to the
To 3
what do you
places.
call it, to the left. Yeah,
Yeah.
and
No,
so then I got 25 times, but that's wrong.
Oh. Well, it's 25 times 1,000, right? Divided by 1,000th is the same thing as times 1,000. Whatever. Do you all
It
get
makes
it
it
now?
positive, is what you're saying. Thousandths to 1,000 makes it positive.
Yeah, you know how it works. Like 1 over 10 to the -3 in your math class is 10 to the power of 3, right?
Yeah.
Okay.
I didn't think of it like that.
Well, now you do, and that's how you should
Yeah.
think. Okay, let's do our temperature in kelvins. Let's go back to that HR diagram. The temperature can be seen here on the x-axis, right?
Right.
So for prox, let's just do 3,000, okay? I want you guys to remember that the lowest possible temperature a star can have is 3,000, and the highest possible temperature is 30,000. I think 3,000 would be a better measurement. How about for Sirius? Maybe 9,000 Kelvin or so?
Yeah.
Yeah, probably around 9,000.
So 3,000 Kelvin versus 9,000 Kelvin. What's our ratio?
3 times.
Okay.
That sounds like a good shirt.
What about the colors?
Is that just what like was showing on the x-axis?
Gotcha.
I'm sorry, Ivy, can you say that again?
Is that just what was showing on the x-axis, the colors at the bottom?
So yeah, it turns out that you remember how Wien's law works, right? Stars have a basic color that's based off their Wien's law. Hold on, let me get a slide to show you here. I might have it in this slideshow. Actually, I probably have it in my light and telescopes one. So if you guys look, just stick with me for a second here. I'm looking for something. There we go, slide 78. Function F5, 78. Stars tend to have one of 3 different colors based on their temperatures. Stars like Betelgeuse, which have a temperature around 3,000 to 4,000 Kelvin, they're basically the same temperature as an incandescent filament in a light bulb. And at 3,000 or 4,000 Kelvin, your black body profile is going to peak somewhere in the infrared portion of the spectrum, meaning you're going to pump out way more red light than violet light, and your star will have a reddish appearance. Then there are stars that are like the sun or so. They peak in the center of the visible spectrum. Now, whatever weed-smoking artist made this illustration, I very much dislike how they call it a yellow star, because if your blackbody peak is around 500 nanometers like the sun, you're actually quite white as seen from space. They're getting confused because our sun looks yellow from the ground because sunlight is being filtered through our atmosphere, where Rayleigh scattering removes blue wavelengths from the spectrum. The sun is not yellow from space. If you look at the sun from outer space, what color is it, class? It's pure white, right? We
Yellow.
saw
Oh, white.
the sun from the ISS. This is what the sun looks like from outer space. It's the purest goddamn white you've ever seen in your life. It only looks yellow because of our atmosphere. So our sun looks pure white because its temperature peak, its Wien peak, as they say, is right in the middle of the visible spectrum. The other possibility is that we could get very blue stars, like the stars you see in the Pleiades. Yeah, that's how I meant to spell it. The Pleiades stars are extremely high temperature, and their Wien peaks are all the way into the they're all the way into the ultraviolet. So when you look at these stars with your naked eye, or if you see them in a photograph, they put out way more blue light than they do any other color. So stars tend to be kind of reddish or whitish or bluish. And sometimes if their Wien peaks are somewhere in the middle here, they can have a slightly yellow appearance. I know that from personal experience, just being out at the observatory. So if we went back there to our HR diagram, what color would you say Sirius is most likely to be? F5, 2.
White.
Yeah, Sirius is a very, very white star. So the color here is red. Color here is white. And we don't have you can't do a ratio there, so just put some dashes, okay? Now stars, as we are going to learn, have a variety of different lifetimes. The lifetimes can be seen here in green. Typical lifetime for Sirius is how many years?
About
10 billion years.
10 to the ninth.
How many billions is that?
10 billion.
False.
1
1
billion.
billion.
1 billion. And how about Proxima Centauri? This is a cartoon, so it's not exactly linear here. Let's just go with the longest span of 10 to the 11. How many billions is that?
That's 10 billion.
False, again.
Oh, 100
Ouch.
billion.
100 billion, exactly. Okay, let's put those into our notes. I'm going to write it in this way. I'm going to write 1 times 10 to the 9 years. And then I'm going to write 100 times 10 to the 9 years. And you can see that the ratio is clearly 100 times longer. Okay, that's it. That's our first problem in a nutshell. I'm ready to move on when you guys are.
Ready. Ready.
All right. Anyone need a moment here?
Give me 30
do.
seconds.
Sure.
Yeah, give me a sec.
That's fine. That means more iced tea sipping for me.
Ice
Yeah, iced tea.
Iced tea.
Okay, Juju. Okay, Juju.
Juju, after what I saw you put up on the screen during our break.
That wasn't that wasn't me. Listen. I don't know drug. That was my
Cock
Oh,
flipping.
I would never do such a thing.
No, you wouldn't. Good thing I had the recording off, huh?
Yeah.
No, there was no recording. That was in
He said-
between the recording. Don't lie.
He said, I do not
No,
consume mind-altering
violate.
substances.
What?
Okay, how we doing here? Anyone still working? Shout at me. Because otherwise, I'm gonna
I'm
erase
good.
it. You're all set? All right, let's do it to it
I can
then.
only speak for me, but I'm all set.
All right. I'm erasing. Morgan, what's our next problem?
Number
55.
55.
54. 54.
Oh, 54? Oh, missed that one. My fault.
That's why, good thing we've got Morgan on task here. Let's see. I think 54 uses the inverse square law, but let me check. Oh, yeah, 54 is about the inverse square law. Do you guys remember that formula? It tells us that the brightness of a star is its luminosity over 4 times pi times d squared, okay? Let's do part A. Suppose a star is the same luminosity as our sun, but is located 10 light years away. So the luminosity of the star is 4 times 10 to the 26 watts at a distance of 10 light years. They want us to find the brightness. How are we going to do that? What units do we measure brightness in, students?
Watts.
That's luminosity.
Oh.
Joule. No, wait, no.
Watts per meter square.
Thanks, Ivy. Watts per square meter.
Watts per square meter.
Do we measure them in watts per square light year?
No.
Nope, that would be weird.
Ooh.
So what are we going to need to do then?
Convert.
Convert it. Dimensional
All right.
analysis. Juju.
All right, let's do that. So we have a distance of 10 light years. What's the conversion factor from light years to meters? Or actually, you guys might not know light years to meters. You might know light years to kilometers. If you know light years to meters, I'll take that. What do you know?
150 times 10 to the 15th.
Oh, that's good. So it's 9.5 times 10 to the 15 meters per light year. Okay, what's that times 10?
9.5 times 10 to the 16.
All right. Now we can plug this into our formula here. Brightness is 4 times 10 to the 26 watts over 4 over pi over 9.5 times 10 to the, 16 meters squared. Take out your calculators and punch them up.
No, you would punch us up on the calculator like you were dividing every problem, right?
That's right. So 4 exp26 divide by 4 divide by pi divide by 9.5 exp16 square key and then equals. What do you get?
3.5 times 10 to the negative 9th.
Units?
Watts per meter squared.
Excellent. Let's box that because that's a classy move. Okay, part B. Part B says, suppose a star is as bright as Alpha Centauri. That is, suppose its brightness is 2.7 times 10 to the minus 8 watts per meter squared. All right, this is getting a little smushy here.
Bless you.
Bless you.
Bless you.
Or as my friend likes to say to me, when you die, nothing happens.
Oh,
Ah,
I like it.
oh. I don't. It's very dark.
But it's located at a distance of 200 light years, okay? And our job here is to find its luminosity. Do you guys have the chops to rearrange that formula for me there? How do I solve for luminosity?
You multiply. Oh no, you divide. Oh, well, yeah. No, you multiply.
no, you were right the first
both
time.
sides by. You multiply both sides by. Hang on, I'm trying. Other people are. I'm trying to see if Mr. Britt's straight. Hang on. You multiply both sides by 4 times pi times distance squared.
Awesome. 4 pi d squared times b. All right, let's plug in our value. Oh, 200 light years. Let's hastily convert that to meters. 9.5 times 10 to the 15 meters per light year. Let's see. 9.5 times 2, 9 times 2 is 18.
1.9 times 10 to the 18th.
Okay. So 4 times pi times 1.9 times 10 to the 18 meters squared times 2.8 times 10 to the minus 7 watts per square meter. What you got? Geez, guys, I'm gonna grow old and die waiting for you to do this calculation.
1.3 times 10 to the 31.
Okay. 1.3 times 10. What are the units?
Watts per
Watts.
meter squared.
No, just watts.
Just watts. That's at least 10 times greater than our own sun. All right, I'm going to erase part A up here. A's going away.
All right.
Part C. Suppose the star has a luminosity of 8 times 10 to the 26. Am I doing the right one here? Yeah, 8 times 10 to the 26 watts. That's double the sun's luminosity. And a brightness of 3.5 times 10 to the minus 12 watts per meter squared. Now, I'm going to help us do some hasty algebra to solve for D. I'm going to flip the distance squared up and the brightness down, and I'm going to square root both sides to create a key formula. In astronomy, we call it the luminosity distance formula. And it looks like this. Distance is the square root of L over 4 pi b.
Yeah. Doing schoolwork.
At the beginning of next week's lecture, I'm going to make a big deal about this, okay?
Okay.
So D equals the square root of.
I'm erasing this stuff, okay?
Go for it.
That works for me.
Let me explain it to you this way, Bozo.
Right?
How many times were you sent to the principal's office? How many times did Miss Baker actually come to talk to you?
We have a luminosity of 8 times 10 to the 26 watts. We have over 4 over
What are you supposed to be doing?
3.5
I should be learning something.
times 10 to the minus 12 watts per square meter. Hey, whoever's arguing with their mom ought to mute their camera or mute their microphone.
That's my brother arguing with my mother.
Okay.
Yeah, it's pretty awkward. I'm gonna be honest.
No, it's fine. Hey, this is the new normal, okay? I want to make sure you guys can hear me, and I want to make sure I can hear you if you have questions.
I'm all alone by
Yeah, I
myself.
feel that.
I got 4.2 times 10 to the 18th watts.
Wait, not watts though.
Oh yeah, because the watts cancel out, right?
Right. Sal, what are the new units?
Meters.
Great. Let's convert that to light years. 1 light year is 9.5 times 10 to the 15 meters. How many light years is that? Oh, box the meters for me, though. How many light years? Jesus, don't make me do this myself here.
I'm doing it right now.
44.
Sorry?
44.
Okay. Can someone confirm that?
I got.
Can confirm. Oh, someone else got something.
44? How about 440?
No.
Yeah, I got 440. 442 to be exact, but to round it off, I got 440.
I got 44.2. Weird. I'm gonna do that again.
Was that you, Michael, who botched that?
I was one of the people that botched it, but I'm gonna try that again.
This is a 15 here, right?
Yeah.
Okay. We got one left.
Oh, one more problem. Thank God.
No, one more.
Yeah, there it is.
I know.
Hey, look, I can only go as fast as you guys go. I can do these problems in 5 minutes or less.
Do it then.
I'm trying to, but I gotta drag you guys along with me here.
Prove it. Prove it.
All right, I'm erasing. I'm gonna keep my superstructure here. We're gonna go to part D. They've made a mistake in part D. I wonder if you guys can tell what it is. In part D, they say the luminosity is 5 times 10 to the 29 watts. And they tell us that the brightness is 9 times 10 to the 15 watts per meter squared. I have to wonder if they intentionally made this mistake. There's something hideously wrong with these givens. Do you know what it is? What's the brightness of Alpha Centauri in part A?
The brightness is significantly less than the luminosity.
Well, of course, the luminosity is how much energy the star puts out in all directions.
Oh, yeah.
Brightness is how much energy the star twinkling on your sky gives you. If you didn't know this, stars are dust. That's why we need light bulbs, okay?
Well, the brightness in part A was 3.5 times 10 to the negative 9
How does
watts
that
per
compare
meter
to the
squared.
brightness in part D?
Isn't it less?
Like, not a little bit, but a lot.
Yeah.
Yeah,
So
it's way less.
what's my
Because it's
point?
in the negative.
Guys, 10 to the power of 15 watts per square meter is fucking insane, right?
Yeah.
If you plug that into your luminosity distance formula, you're going to find that that star is located 10 kilometers away in Boston, which would be problematic. What mistake did they make?
Maybe they're
We
supposed
did
to
a
have.
negative 15.
Yeah.
That's right. That's right. All right, let's plug those numbers in instead. The distance is the square root of 5 times 10 to the 29 watts over 4 over pi over 9 times 10 to the minus 15 watts per square meter. Punch them up.
Isn't it 4.9 to the times 10 to the 53?
53? Did you? That sounds too high. I think the radius of the universe is 10 to the 20 meters. So that's the
I might have put it down wrong.
I got 4.9 times 10 to the 56th.
No. Are you forgetting the square or you're
I
forgetting?
did square
I
it.
did squared.
Did you square root it?
Yes, I did.
If I have
Oh, I didn't. Okay, now I got 2.2
Why are we
times 10
squaring
to
it?
the 28th.
Why are we squaring it?
Oh, because I fucked up. That's why. Sorry. We're not. Thank you, Anakin
Oh my
and
goodness.
Morgan. We're not supposed to be squaring it. All right, so that's probably why we're getting it wrong. I'm sorry, guys. I was used to doing the other. I was just testing you to see who the best students were.
Yeah,
Right.
Remember when he was bragging about being
I
able
believe
to
it.
Bunch of apps coming from you. It's all that iced tea he's drinking. It's
I have
definitely
one.
that iced tea edition.
I'm so
So-
baffled. Okay. I've been talking smack, and now you guys got me. What's the final answer?
I think it's still
2.1
pretty.
times 10 to the 21.
Thanks, Hope.
How you guys?
And that's what my units, Hope.
Maggie, or no?
So cute.
Is it meters?
That's right.
You feel me?
How many light years is that?
Maggie.
How many light years?
Is that 21?
I'm gonna find out through dimensional analysis.
A lot.
5 times 10 to the 51. Yeah. So,
She says,
Why is my thing on stop?
oh my god.
Professor, can you say something?
Me?
If you like double tap on him in gallery mode, it makes him the active person again.
listen, bro. If she
220,000.
finds my shit, bro, I'm taking one of his bitches.
Jonathan, how many light years? I like your solar background there, but all right, now I'm gonna look at all your faces. Zach, you gotta keep
221,052 light years.
220,000.
Yeah, bro. Like they're FaceTiming each other, bro.
Jesus.
Okay.
It's far
That's
away.
really
Second
far.
question down the hatch.
Listen. I told him now, listen. My shorty,
Yay.
shorty doesn't call me back, bro. If I call her, bro, she doesn't pick up, bro. I'm taking one.
I'm ready to move when you guys are.
That's exactly.
I'm ready.
Ready.
And now it's 55.
Sorry, Morgan?
Now it's number 55.
Successfully.
Now it's 55. I got you. Okay, I'm erasing.
Come on, I gotta make sure she's with it. Gotta make sure that this black girl, she's really with the shit because
Yo,
now
I
stop
gotta mute
talking
you
to me
down
now
there.
because no.
Hold on. I still have the equations written down, but it wanted that in both kilometers and light years. We got it to meters.
Forget about kilometers. I relieve you of kilometer command.
Okay.
There's no point in converting to kilometers. Light years was worth it, but not kilometers, okay?
Okay. Yep.
I appreciate your attention to detail, Riker. I just figured we could skip the
No,
kilometer.
that's fine. I just figured I'd mention it.
Yep.
That was all.
Keep me on task, okay, buddy?
Yep.
Okay. The next problem is really simple. We haven't gotten to the formula. Sorry, I'm trying to focus myself here. It's on something called parallax. Now, I'm going to explain how this formula works next time. So parallax is a technique to measure the distances to stars. The formula is
the villain in the Green Lantern movie.
the distance measured in a unit called parsecs is 1 over the parallax angle in arc seconds, where d is the distance in a unit called parsecs. 1 parsec is 3.26 light years. Okay?
Hold on. So distance in parsecs.
Yep.
Is that what that is? Because I can't really read that very well.
Yeah. Hold on.
No, the actual equation itself. Is that a PC?
Yeah.
Or a parsec? Okay.
Is that better?
What's next to the D? I meant next to the P in the equation, in the parentheses, a denominator.
Forget it.
Okay, thank you.
Now this letter is a Greek letter called rho, but it kind of looks like a P, so I use it for the parallax angle. Rho is the parallax angle in arc seconds. You guys got this, Jazz?
Not yet.
Alpha Centauri is our first star. Alpha Centauri has a parallax angle of 0.7420 arc seconds. We need to find the distance in parsecs and light years. The distance is 1 divided by the parallax angle. I'd like to introduce a new key on your calculator that comes in handy sometimes. It's known as your reciprocal key. It's, let me see if I can focus this. It's above the closed parentheses. Come on, focus, you dork. It wants to focus close when I'm far away.
It's the one left of XY.
Yeah, but it's in the orange. It's 1 over x. It's up here. Right there. So type this in with me. Just type in 0.7420, and then we'll hit our reciprocal key. Shift, and then close parentheses to get 1 over x. What do you get?
1.348.
Parsecs, right?
Yep.
And now let's convert that to light years. You know what, guys? Forget about the precision, okay? It's ridiculous. 1.3 parsecs.
Okay.
And that's 2.26 parsecs. How many light years is, oh, sorry. Got it wrong, got it
Yeah, I was
backwards.
gonna say what?
1 parsec is 3.26 light years. How many light years is that?
Four 4.2.
4.2?
4 light years.
Like,
I was hoping to get 4.4, but maybe it's because I shaved off the.
Oh, no, I got 4.39, so yeah, it would be 4.4.
Okay. That's, I mean, Alpha Centauri is 4.4 light years away, right? So whoever got, if that was IV, 4.2 was, something funny happened there. Question B. Procyon, parallax angle of 0.2860.
Don't erase anything yet.
I won't. Our distance is 1 over 0.2860 arc seconds. Someone want to do that? Ah, someone want to do that one for me? My bolo tie just got caught in a milk crate. Big problems here.
.5 parsecs.
Okay. How many light years is that?
.2.
3.26 light years per parsec. 11.2, sorry. I can't write when I'm this crunched over here.
11.4.
Which is it?
11.4.
Okay. That looks good to me. Bam, third problem, down the hatch. We're rapidly approaching cocktail hour here in the Britton household.
Yeah.
So in this homework set, one of the reasons why I wasn't so worried that we were doing it before chapter 15 is there are only 2 problems whose formulas you've not seen. This is one of them, but the formulas are really, really easy. The next problem is another new one, but the formula is also easy. And then the last problem is just an NK3 problem. It looks like a lot of you are sort of done writing. Let me just kind of scroll through the people's faces here. I can't see everyone's video, but those of you that I can see look like you're good. So can I erase and move on?
Yeah.
Is that,
Yeah.
Tim's got a
Yeah.
thumbs up.
Affirmative.
Okay. I'm erasing.
Erase.
Shoot. Oh boy. Huh. What did I do with the eraser? Okay. Oh, here it is. Okay, jeez. Okay, this next problem is unfortunately some new stuff, but it's not overly complicated. It's on something called the magnitude system. Chapter 15, number 56. And it's about something called apparent magnitude. The symbol for apparent magnitude in astronomy is a lowercase m. Apparent magnitude is a measurement of brightness by eyeball. Sorry, my autofocus is going crazy here. This camera kind of sucks, honestly. Look at that, it's focused really close.
Huh. That's so bad.
Hold on.
We can work with this.
What kind of camera is it?
I can't manually control it, so I'm just trying to give it something to latch onto. Moving back, there we go.
Didn't you just get the camera too?
Yeah, and I paid like double what it was worth because there's a shortage in cameras. So I thought it was going to be awesome. I thought it would look this clear all the time. But
Can
there's
you use your phone?
Then there's like a tiny little window. Yeah, I can, but it won't cover the, like, do you see how wide this is? That's good.
Oh, I would just put it horizontally, you know? Probably.
That works.
Maybe.
But if you want to see our beautiful shining faces, that might be a different story. You know?
I like to see shining faces. All right, anyways, look. Here's how apparent magnitude works. It's a ranking of stellar brightness. There are no units. It's just a raw number. It's kind of like amihotornot.com for stars. The very brightest stars, we give them an apparent magnitude of 1. The second ranked brightest stars get an apparent magnitude of 2. The third ranked brightest stars get a magnitude of 3. And all the way down to the faintest stars that you can barely see, the dimmest stars that you can see in the sky get an apparent magnitude of 6. So if you've ever ranked your top 6 favorite movies, this is the same thing. It's the top 6 brightest stars in the sky, okay? Now, unfortunately, the person who invented this system, an ancient Greek named Hipparchos, kind of made us an unfortunate choice of using very small numbers to represent bright stars and larger numbers to represent dim stars. And it turns out that a change in 5 magnitudes corresponds to a ratio of 100 times in brightness. That means a magnitude 1 star, like the star Sirius, is 100 times brighter than a magnitude 6 star, like Proxima Centauri, okay? So here's the equation that we need to go from magnitudes to brightness. I want you to write this down. To convert between the two, let's imagine that we have 2 stars. An A star, which is the brighter star, and a B star, which is the dimmer star. We're going to use A and B here. If I want to know the ratio in brightness of the A star to the B star, I've got to take the number 100 and I've got to raise it to the power of the change in magnitudes divided by 5. Where I've used the delta magnitude here. That is 100 raised to the power of magnitude B minus magnitude A divided by 5. I'd like to point out to the class that the ratio here is A star to B star because A is brighter. But when we subtract the magnitudes, it's magnitude B minus magnitude A because the B has the larger magnitude. Magnitudes can be confusing. Whatever. Let's just try part A together. Which is brighter in our sky? A star with an apparent magnitude of 2, which will be the A star, or a star with an apparent magnitude of 7, which is the B star. And we want to calculate the ratio of their fluxes. How many times brighter is the magnitude 2 star to the magnitude 7 star? Can you guys tell me how to set this up?
2 over 7.
No.
No.
This is magnitudes, not brightness.
Oh.
7 minus 2 over 5.
All right, that's good. So let's set it up like this. The brightness of the magnitude 2 star to the brightness of the magnitude 7 star is the power of, the number 100 raised to the power of just what you guys said. 7 minus 2 divided by 5. What does that turn out to be?
100 times.
It's just 100 times.
That's right. It's 100 to the power of 1, which is 100 times brighter. So we could say a magnitude 2 star is 100 times brighter than a magnitude 7 star. Write that down next to your 100 times. Can you guys read that nonsense?
Yes.
I got kicked out, so I missed most of it, but I can read it.
Sorry?
Disconnected first.
Oh, they got kicked
so I
out.
can get out.
Who got kicked out?
Just got disconnected. Stuff
Oh.
on mic.
Are you back, Zach?
Yeah, I can see everything. I'm back in.
Okay, cool. I'll give you a second to copy and catch up.
Thank you.
Remind me to save the chat log too.
Let me see.
Oh, there's not much of a chat. You guys don't chat. The other group chats a lot. You guys don't chat log.
Are they the tag twos? The
They're the cat crew. You guys are the dog crew.
I have my cats. They just like not around me right now.
Yeah, I like it when you guys bring your animals onto the screen. It's funny. One of the guys in the 1010 class has like a lizard, and he puts the lizard up to the camera. It's pretty funny.
Ha 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 ha. That's funny. Ha 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 ha.
My dog's personalities are
Raph, mute yourself.
Oh, shut up.
Say complete.
Is everyone doing all right?
Yeah.
Yep, almost done.
I'm good.
Let's chat.
Oh my God.
Okay, can I erase?
Yeah.
Yeah.
Wait, was that a no?
Affirmative.
I know. I used to put the stars on your head.
Really?
Wait, I'm sorry, that's a little confusing. Does anyone want me to keep that stuff on the board?
This thing's almost a
I already
decade
have it
old.
down.
Almost 2 decades old.
All right, I'm erasing.
I still love it.
All right. Next up, we're going to do something called absolute magnitude. Absolute magnitude gets a capital M. It's kind of like apparent magnitude, but they all have the same distance. So absolute magnitude is a tracer of luminosity. And the formula is exactly the same. The ratio of luminosities from an A star, which is brighter, to a B star, which is dimmer, is 100 to the power in the change of absolute magnitudes divided by 5. So in question B, they say to us, which has a greater luminosity? A star with an absolute magnitude of -4, or a star with an absolute magnitude of +6? Which of those is the more luminous star?
Probably +6.
That would be wicked wrong. That's not how magnitudes work.
Magnitudes work. The smaller the number, the greater the magnitude.
Extending all the way into the negatives. Do you know what the apparent magnitude of the sun is? -27. Magnitudes are freaking confusing. That's why we're going to have a big lecture on them next week. Okay, so the luminosity of a -4 star to the luminosity of a +6 star is 100 to the power of +6 minus -4 divided by 5. What's
So 200. Oh no, 1,000.
All right, we better do this one slower. What's +6 minus -4?
10.
So that's 100 to the power of 10/5, which is 100 squared. What's that equal to?
1,000.
False again.
Oh, 10,000.
Thank you. 10,000 times. We can say a absolute magnitude -4 star is 10,000 times more luminous than an absolute magnitude +6 star. Woo! 4 down, 1 to go.
Can you keep it on the board for like another minute?
Yeah.
Sure thing. Okay. There's a big snack waiting for me on the table, so we better finish this last problem.
Just hang on.
Is it a cookie?
It's actually hummus and tabbouleh and baba ganoush and salad. I'm kind of getting spoiled rotten today.
Oh man, he said hummus. I bet you go to Whole Foods.
He's a Whole Foods shopper. He looks like
I bet you go to Whole Foods with flip-flops
I'm one
on.
step more bougie than that. There's a little Greek restaurant called cafeteria called Yoleni's, and it's just a block away from my house. And if I just walk a block
in the
away,
arcade,
I can get super fresh hummus and tabbouleh and baba ganoush and all that stuff.
That it's some Middle Eastern
Baba
stuff. I
ganoush?
think, right?
I'm a bubble tea person, so I can't even get any right
No,
now.
that place is in the arcade. That place is nice.
That's how I feel about heroin.
Right?
All my heroin dealers are inside.
Is that what you're having for lunch, Michael?
What did you just say? Heroin?
A nice full plate of heroin.
All right, look, hey guys, this is being recorded, and shut the hell up.
Right.
Okay.
God damn.
God,
I'm erasing here.
Do you have any police officers in your
Remember,
class?
you can erase.
I'm not erase.
Is everyone good?
Yes,
Sally,
sir.
you good?
Yeah, I'm good.
All right, here I
Oh,
go.
better be good. You couldn't just take a
Watch
picture.
the video if you didn't get it. Okay.
Can we just take photos of your screen and send you that as our homework?
No. Like, look, at least write it.
Oh.
I'm doing your homework for you. The least you could do is copy it, you know? I wrote it
At
down.
least retain some of the information.
Just write it down. Writing is good for you, you know. This works your brain. Stretch your brain. Don't become flabby in the mind, okay? Okay, last problem is number 57. We're going to calculate a binary star mass. Or should I say masses?
How many parts are there to this problem?
That the spectral lines of two stars, so the Doppler shift of two stars, we have a Doppler shift measured for absorption lines in stars. And they tell us that we have equal shifted lines. That's one of our givens. They tell us that the period is 6 months. And they tell us that the velocities of the two stars, when you apply the Doppler effect, is 8,000 meters per second. Now we're going to draw a little cartoon together of how this works. I have one star, the mass of star 1, and a smaller star, M2, is orbiting around it in a quasi-circular orbit, okay? The radius of the orbit is A for semi-major axis. And our goal is to measure the masses of the two stars using Newton's version of Kepler's third law. The total mass of the system, the mass of star 1 plus the mass of star 2, is equal to 4 times pi squared times a cubed divided by g divided by the period squared. First thing we're going to do is we're going to convert the period into seconds, because this formula requires MKS units. How do you think we should do that? I'm starting with 6 months. What should I do from there?
Weeks. Or you could do days.
That's even a bad idea, because months are a terrible unit of time. Months do not have a constant number of days, right?
Yeah, so it should be weeks then.
I still think that's a bad idea, because the number of weeks aren't constant either. I think we should
5 years.
back convert it to years and then forward convert it to seconds. So 6 months is how many years?
Half a year.
0.5 years.
Sorry. Yeah. So 6 over
It's gonna
12
be half a year.
is 0.5. Do you guys remember how many seconds are in a year?
Oh, shoot. I have this in my notes.
It's 3.15 times 10 to the 7.
Yeah, good job,
7.
Marcus.
Yeah.
Nicely done.
That's what's up.
Times 10 to the 7 seconds per year. Okay, get me the number of seconds, class.
Calculator.
Jonathan, are you calculating?
1.6 times 10 to the 7th.
All right. Units?
Seconds.
Good. So that's our period.
Actually, yeah, no, that's right. Okay, now that I'm confusing myself. Don't mind me.
I'm going to have to erase my givens up here because I need a little more board space.
All right.
Now listen, we're going to make an argument. Imagine this star goes around in a circle. I'm going to derive a new formula for you. Do you guys know what the circumference of a circle is in terms of its radius?
T equals 2 times pi r.
Who knows their geometry? Anakin, do you know any geometry? What's the circumference of a circle?
2 pi r
365 degrees.
2 pi r, right? Very good. But in this case, our radius is a. The circumference of this orbit is 2 pi a. Imagine the mass goes around, and imagine doing distance equals rate times time. The distance is the circumference of the circle, the rate is the velocity, and the time is the period. And I can rearrange this formula to solve for A and come up with a critical formula for binary stars. For circular orbits, the radius of orbit is the velocity times the period over 2 pi. This is a new formula in chapter 15, and I call it the binary star orbit formula. We're going to use it to calculate our A in meters. May I erase this nonsense?
I got it.
1 second.
Yeah.
Someone said 1 second. Somebody wait a second.
Okay, I'm good.
All right. Anyone else? Let's calculate the radius of orbit. A equals 80,000 meters per second times 1.6 times 10 to the 7 seconds divided by 2 divided by pi. I'll take that answer at any time.
I got 2.0 times 10 to the 11th meters. I mean, not meters. Actually, is it meters?
Oh, he left. He thought you would take longer.
Probably.
Little faith.
This pita bread is warm.
Okay.
So that's heaven. That's heaven.
So I got to rub it in. What'd you get?
It's like that's heaven.
I got 2.0 times 10 to the 11th.
Units?
meters.
No. Oh, what'd you say?
10
Meters.
to the 11 meters. Yeah.
Correct. All right. Now we're ready to apply NK3. The total mass of our system.
Boy. The big boy.
The big boy.
Formula.
4 times pi squared times 2.0 times 10 to the 11 meters cubed over big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the period 1.6 times 10 to the 7 seconds squared. Okay, you guys remember how to do this from back in the day? Show me what you're made out of.
You divide
Mostly carbon, I think.
by this 7 divide by. Well, that's the good thing about this class too, bro. They help you with your like calculator skills, bro.
Okay, what you got? You know, I'm always watching you guys eat while I'm teaching. Time for me.
I got 1.8 times 10 to the 31.
That sounds good. Hey, you know what? Hey, Bella, let's keep it simple. Let's make it just 2 times 10 to the 31. Right?
Meters squared, right?
Nope.
Or just meters.
Oh.
What'd you say, Morgan?
It's just meters.
Nope.
No? Oh, kilograms.
Kilograms. Look, meters cubed, cancel with meters cubed. Second squared, cancel with second squared. 1 over 2 kilograms is kilograms. Let's convert that to solar mass units. Up here, I'm going to convert it to solar mass units. 2 times 10 to the 31 kilograms. Do you guys know what the conversion is from kilograms to solar masses? What's the mass of the sun? How many kilograms does the sun equal to?
2 times 10 to the 30th kilograms.
Thank you. Was that you, Hope?
Yeah.
Thank you. So how many solar masses are we talking here?
10.
Yeah. Now, they want the mass of each star. If the stars have equal Doppler shifts, that implies that mass 1 is equal to mass 2. What is each mass equal to? Whoops.
5 solar masses.
Nice. And that, friends, is a wrap.
Oh.
Give everyone a moment to catch up and copy all that down. So I pushed us kind of hard this session, but I wanted to try to get done in less than an hour and a half. It's been taking about an hour and a half to do these problem sets.
What did the bottom of that say? Oh,
where, Riker?
7 times 10 to the negative 11th meters. Oh, meters cubed over second squared.
Meters
kilogram.
cubed per kilogram per second squared.
Per second squared. Okay.
I've got a feeling like this chat log is going to be funny.
No, no, it's not. I don't.
That much.
Just ignore it. Just ignore it.
Just to let you know, I heard that Zoom actually keeps the chats and all the professors can actually see, even the private ones.
Oh my gosh.
Oh.
Yeah, so Michael, let's not be typing up. Thank you, Bella. My friend Zaz is dead set against it, so I really trust his expertise and his wisdom when it comes to technology stuff. He's a cool cat. So we'll try to find one that's equally good. But for now, Zoom is working, so I'm sticking with it until I have a better option.
Yeah.
I mean, normally I don't have anything to hide, so I don't mind if. Well, okay, no. Privacy and security are important. I don't think people should have access to your data without your permission. That's wrong. But in our class, we're doing something very good and wholesome here until Michael opens his mouth. So.
Or Raph.
Or Juju. But those guys, you know, we'll keep them in line.
You can try.
Hey,
I am a wild card.
Let's
Alright,
go to gallery mode to wrap things up here. Okay, how we doing, everyone? We cool?
Yeah.
Like a cucumber.
Nice. And are we all gonna submit our homeworks to the homework submission section and our labs to the lab submission section? Yes.
Yeah.
Also, don't forget, friends, I need a format that we can work with, right? Like, I need to get a JPEG or a PDF, something I can read. Oh, can I ask one other favor? Can we try to submit them on, I try to do my grading on like Sundays at the last possible minute when I'm feeling really grouchy. So a bunch of you turn in your work from last week on like Monday, probably because you were like, oh, I should get my stuff together. And I totally understand that because I am a lifelong procrastinator. But try to get it in right away or by the end of the week or something so that I can get everyone graded. And I want to figure out, some people just aren't signing in and they're not submitting work. I want to try to hunt them down and like antagonize them so that I don't have to flunk them at the end of the semester. So keeping up with just the submissions, I know it's irritating, but if you could do that, that would be wonderful. It's nice to see some nighttime people here too, Mike and Jenna and Amber. Thank you for being a part of the crew. Oh, and Morgan. Thank you for being part of daytime crew. And thank you guys for sharing your videos because I like to look at your faces and see your funny.
Sorry, I butt dialed you.
Oh, that's okay.
Sorry about that. I currently have the coronavirus, and everyone in my family does, so I look like hot shit.
Wait, do you really have the coronavirus? Oh my gosh! Is it?
My parents are positive right now, and I am currently symptomatic. So I can't.
How does it feel?
Are you dead ass?
I'm dead ass. I can't even be more serious.
Does it feel worse than a normal cold?
My parents ain't really doing too well with it. Like they are currently like a week in, and the second week is where it's supposed to get really, really bad.
Oh wow.
But as of right now, all it is like a slight headache, some nausea. It's really not that bad for me at the moment, but I don't know. I personally.
A couple of people I talked to said they lose taste and smell for a little bit.
Yeah, that's what my parents are kind of like. Like they haven't really been eating over the last couple of days because they're like, I can't taste anything.
Oh my gosh. Well, you gotta keep your salts up and stuff. So, geez, Marcus, I'm so sorry to hear that, but I'm glad you still have the energy to be with us and do some astronomy. That's cool.
Marcus is a real one.
Big bull. Big bull.
Bags, just kick out the corona.
Real one, bro. He's a real one.
Hey, I mean,
savage.
Honestly, if you think about it, guys, doing this little class every day, all of us are locked in our little worlds with not a whole lot to do, you know? It's been nice to kind of come to class and have a little we need to try to stay normal as much as we can. And in a way, coming to class and doing this thing is a little bit of normality. And I mean, we're talking about me here, right? So if I'm normal, then you're all really in trouble.
We're screwed.
But anyways, Marcus, you fight that beast and drink some water. And the good news, Marcus, is once it's over, you're going to be totally immune to that bullshit, and it's not going to be
clear for the season. Yeah.
So I think one of the nice things about getting it is,
and then you get to laugh about us.
You can just you'll be invincible after that, which is cool.
Yeah, my hopes is that if it does pass, like I'll be able to like go out and everyone's still in quarantine and I'm just like skim it down.
Well, just make sure that you're not contagious anymore because.
Yeah.
Hey, that's a good point. You know, I don't know what the contagion window is, but probably it's still there a little while after you feel better. So maybe just stick to a solo bike ride or something until.
Yeah.
I heard some people are asymptomatic, so they don't show any symptoms at all, but they have the virus.
I know, it's so scary. That's what makes it so evil. Is the really long incubation period and the asymptomatic shedding of the virus. It's such an evil bug, you know.
Yeah.
But,
Marcus is probably like, man, I wish I was asymptomatic.
Oh, hey, by the way, I should mention, if you guys didn't get the message from CCRI, that I got an email saying that our entire summer 1 class is going to be online as well. So we're going to be doing it for a while. If any of you are planning on taking summer classes, I teach both versions of my course, summer 1 and summer 2. So I'm looking at another semester of this, and if you guys are taking summer classes, you are as well. So.
Well,
I'm graduating.
Technically, I should have graduated this semester. If all my online classes still, like, if I'm able to pass them all, because they're kind of weird, then I should graduate. But I was like, if this all fails, I can do I can do a summer class, but apparently that's going to be online too. So.
Well, I know that sometimes professors aren't so good about doing the summer classes right. I tried to make ours as much like the class as possible, where we can kind of do our labs together and do our office hours together. The doubling of the midterm was a big question that still hangs over us. I think it's probably the right way to go because all of you guys have a midterm grade. And if you double it just by doing labs and homeworks together, it'll make sure we all pass. Remember, anyone who wants to take the final exam for some reason, I'll work that out with you. So I'm not saying you can't take it, but I'm saying if you'd prefer not to.
Hell yeah.
Yeah, I'm thinking about just doubling your midterm grade and being done with it. That way we just kind of come every week, we gather together, we do a little work together, and that way it's easy to get through this, you know? Okay, well, awesome hanging with you guys. I guess I'll see you on Tuesday, right?
Yep.
Y'all take care of yourselves, especially you, Marcus.
Before we send off,
You too, Professor.
I have like an astrology lighting.
Taking pictures of all my homework.
I'm gonna don't forget to submit your stuff. I'm gonna save this chat before I forget.
By the way, you never showed us the plutonium or whatever.
Oh yeah,
it's okay.
Man,
You
I
don't,
really
you
want
don't
to
need
do
to
that.
save
So,
the chat. It's fine.
Yeah, can you show us?
so this is a rock of.
Dude, I told you to get rid of that.
Yeah, I know.
I told you a year and a half ago to get rid of that.
This is a rock. It's a sandstone that's from Arizona. Let me go to speaker view here and look at the beautiful yellow coloring of this. Let's see if I can get it nice and close. This
Don't
let me see if I can get it
near
in focus. So do you see how
feel the radiation through the screen?
Yeah.
Yeah, I can feel
Well,
it.
this
in
is
my
actually
heart.
quite radioactive. Which is why it's like, so here's my Geiger.
I know. I've been telling you to get rid of it for 2 years.
This is a Geiger counter which measures radioactivity. You guys remember the 3 types of particles that are given off in radioactivity, right? What are the 3 types of particles?
Alpha particles. I don't know.
Beta
particles.
Beta. Yep, beta and gamma. I knew it.
Alpha particles, electrons, and gamma rays. And this measures them. Let's see. You'll have to be quiet. Let's see if we can hear the clicks. Can you guys hear the clicks?
Yeah.
That first one.
No.
They come in at random intervals.
Oh, wait.
Oh, yeah.
Now, that means there are radioactive particles in my house just flying around. There's always a bit of radioactivity everywhere. Let's hold it up to the samples and see what happens. So here are my sample tests. I have 3 little sample charges here. Ooh, that just got a spike. This is, I should definitely wash my hands after all this. This is strontium. I'm trying to get it into focus here. Come on, focus, you jerk. This is strontium 90. I wanted you to be able to, oops. Okay. Wait, let's go to cell phone mode here. Share screen. Oh, I've got to go to my Wi-Fi. I don't have to worry about coronavirus because I'm totally going to die of radiation poisoning before that. Here we go. Wi-Fi on. Okay, so I'm joining my network. I'm going to share my iPhone with you guys. What a plugin is
Technology, man.
No, I already have the plugin.
You know what's
Oh, here we go.
Never mind. Figure it out. My cousin's a computer with, so he knows how and everything.
It's loading. Okay. You see my iPhone now?
Yeah.
Yeah.
Yep.
Well, that works perfectly.
Okay. So let's hold this up. Can you hear the clicks?
Yeah.
Yep. All right. Strontium 90 is kind of all right. Let's try another one here. Let's try polonium 210. Do you guys know about polonium? This is what they killed all those Russian agents with in England. This stuff is pretty nasty. This has a rapid short life, a short half-life. So I suspect it's, hold on, I'm trying to do something with 3 hands here.
Wait, how fast does it decay?
On the order of months or something.
Ooh.
Here, cobalt 60. Let's try cobalt 60. This has a longer half-life. I need to wait. I'm trying to like hold this steady while also holding my Geiger counter here. Oh shit. Can you hear that?
Yep.
Yeah.
All right. Now I'm going to leave it up here so you can hear the clicks. Let's go over to my rock of uranium.
For the mad lad.
Oh wait. I need my
They're printed out 2 sheets.
Okay, here we go. So listen for the clicks. Can you hear that?
Yeah.
Yeah.
Now,
how radioactive is that? Like, what's the number?
Really, really, really radioactive. Like, really, like dangerous, bad for you.
Why do you? 2 years I've been telling you to get rid of it.
I was told that this box here was supposed to shield me.
Well, test it.
Find out.
That box doesn't protect you at all.
So hold on, exactly. Now, I got this box, which was supposed to be a lead lined box, but it was lead foil lined. So let's put it in the lead foil box.
So she's been scamming a long time. Getting over my opinion.
Okay, you ready? Let's see how the
Yep.
box does.
If someone would take advantage of anybody that you saw was a good one, some could use the term gold digger.
Wow.
Not enough.
That's
Not
why
enough.
I'm going to take this. I'm going to hide it way over here.
Yeah, that's why you keep it in your desk that you sit at all the time.
Okay. Anyways, it's more fun when I get to irradiate the students, but unfortunately, I'm just irradiating myself and my guest here. So,
How much is a Geiger counter?
a couple $100. Although my buddy Zaz, who was with us earlier, he actually has a kit and he built his own Geiger counter, and it's really beautiful. Maybe I'll ask him if he can share that with us. If any of you are electronics hobbyists, you can build your own Geiger counter, and it was quite beautiful, the one that he made. He was very excited when I told him I had a rock of carnotite because he wanted to take his home-built Geiger counter over and listen to it go click, click, click on my radioactive rock.
Yeah, there's like an area near my house that's like blocked off, and I guess like in the 50s or something, there was like an accident with some nuclear material in a plant or something.
Huh.
And I was curious. I might go over there with a Geiger counter.
Yeah, you should find out where that is, and maybe I'll go there with the Geiger counter too, and we can explore it. I know, you know what some people do to collect radioactive materials? There used to be a glass factory around here. I think it was Crown Glass, and they used to dope their glass with uranium to give it this beautiful blue tint. So people who are like antiques collectors will sometimes go for looking for uranium leaded glass in like antique stores around Rhode Island, and you can find these beautiful blue glass bottles which are totally radioactive, and if you put them under a black light, they phosphoresce and glow. Or if they fluoresce and they glow. They're really beautiful. Anyways, okay guys, I'm gonna wash my hands really carefully and eat some hummus. I'm gonna stop the recording now.